Yeah, so this is the first video on FET biasing, that is field effect transistor biasing. So here in the first video, we will discuss about some basics of the FET biasing, that is how the FET biasing that differs from the BJT biasing or how it is similar to that. So both the things will be discussed here. Okay. So let's say few basics we will discuss. Yeah. So fats have to be operated in the pinch off region if we are using it as an amplifier. In case it is used as a switch, for maximum current it should be in one state, and for the minimum current it should be in the other state. That is two extremes of the biasing curves. Okay. For BJT, say the Q point we know that has to be established at the center of the DC load line. Similarly, for FETs, the output current and output voltage they have defined at that is center of the DC, that center of the maximum voltage. That means IDS, that is ID, output current ID, that should be equal to IDSS, that is the maximum current, right? When VGS is equal to 0, this is specifically for JFET. Okay, this is for S, this IDSS. Similarly, VDS, the output voltage, VDS, that should be equal to VDD by 2. That should be equal to VDD by 2. Fine. Now, how we find the Q point in BJT? We are using actually the output characteristic. Oh, that is on the output characteristic, we are imposing the conditions of the input. That is different IB currents they are imposed on it, because we know in case of BJT IC that is equal to, it is a function of IB. Okay, so the output current IC is controlled by IB. In case of FETs, the output current ID is controlled by the, in case of FETs, the output current ID is controlled by the VGS. It's a function of VGS. And so, and there is a direct relation, that is there is a direct transfer characteristic is there, which is representing VGS ID versus VGS. So we will be establishing the Q point on the transfer characteristic. Okay, operating point will be set on the transfer characteristic. Okay, not on the output characteristic. Okay, though we are interested in the output only. So at the Q point, when the FET is operating at the Q point, what is the output voltage and output current, that we are interested in. But for the conditions, for theoretical conditions, that is for the understanding for analytical purpose, we will use the Q point by definition is on the ID versus VGS curve. Means it is ID versus VGS curve. One more thing, that is in case of BJT, that is IC that is equal to beta IB. So the relation between input IB and the output IC, that is linear. You can see Y is equal to MX. Fine. So this is a linear relationship. But in case of FATs, the relation ID with VGS is not linear, right? In case of JFET and D MOSFET, it is ID that is equal to 1 IDSS into 1 minus VGS over VP whole square. Okay, and similarly for E MOSFET, this is equal to ID is equal to K into VGS minus VT over square, where this K is a constant. It is called conduction constant, conduction parameter, and it is depending on the temperature, because it also depends on the mobility as well as the applied electric field as well as the physical dimension of the channel. Okay, and VT, that is the threshold voltage on the characteristic from which the gate source voltage which is sufficiently required, that is minimum required to make the E MOSFET active, that is to have sufficient ID current, right? But here see, in both the cases you can see that is the id that depends on the square of the vgs. Somehow it is square of the vgs. Once again, see here idss, that is the maximum saturation current, as well as vp, the pinch of voltage, the threshold voltage. These are, or k, these are the constant defined by the manufacturer. Okay, and so the only variable that is VGS, that is ID, depends on the square of the VGS on this equation, and similarly it also depends on the square of the equation, square of the VGS in this other equation. So in both cases, whether it is JFET or DMOSFET or EMOSFET or in general in any FET, that is ID is non-linearly proportional to the VGS, that is the controlling parameter, or non-linearity, that is actually quadratic. Fine. Yeah, few more basics about the FATs. That is, see, you can see what happens. Let's say this is a FAT. There are three terminals. That is a source, gate, and the drain. The drain current and the source current, and this is the gate current. Now, see, because we know in any case the FAT that is having on the input side, there is a insulating material, okay, that offers very high input impedance. Okay, insulating material SiO2 layer is there, and that is very thin though, but that offers very high input impedance, so that the current Ig entering to the gate terminal is almost zero. The current Ig gate current entering to the gate terminal is almost zero. Okay, negligible. Second thing is the ID and IS. Okay, we know that by construction, source and drain are having the same channel through which the current is passing from source to the drain. So whatever majority carriers they are flowing from the source to the channel to drain, that is constituting drain current, that itself is constituting the source current. So ID is same as IS. So these are two things too, that is Ig is equal to 0 and ID is same as IS. These were the two things which are specific to FAT. Okay, and these were not, such conditions were not there in case of BJT, but this adds some simplicity in the analysis. Okay, also you can see this is the gate to source voltage and this is VDS. How you can define? By definition, when you say it is VGS, that means G is plus and S is minus by definition. Fine. Okay. One more thing, so that is we say that is q point, that is equal to, we are defining it not by VDS and ID combination, but it is defined as VGS and ID combination. Of course, VDS corresponding to this q point has a specific importance. Okay, so how you find out the decide the operating point in case of the uh, in case of the FATs? Okay, so we know we have to use a transfer characteristic. Okay, also VGS is a controlling voltage. This is one more difference, which is kept negative in case of JFET and DMOSFET, and it is kept positive. Control voltage VGS is kept positive in case of EMOSFET operation. So in case of JFET as well as EMOSFET, this is going, sorry, DMOSFET, this is going to be the configuration, that is VGS is the negative and this is, so this is actually the transfer characteristic of a junction FET, JFET. Okay, transfer characteristic of a junction FET. We know the equation which is governing, that is IT is equal to ITSS into 1 minus VGS over VP square, where VP is the pinch of voltage. It is also called VGS for off voltage, that is gate to source voltage to make it off. Okay, so that is, there is almost no current passing when VGS is less than, that is even less than VP. Fine, and this is the quadratic relationship between VGS and ID. ID is quadratically changing. Fine. Yeah, so you can try to understand, that is, if you take VP is equal to VGS is equal to, suppose VP by 2, VP by 2 is somewhere here. If it is VP by 2, that is 1 minus VP will cancel, that is 1 by 2 square, so it is IDS by 4. That means ID is not at half point, but ID will be at the fourth point, that is IDSS by 4. So that's how this is actually a non-linear. Okay. Now, how to decide the Q point? Okay. So first select a convenient value of drain current. Okay. Because we have to decide IDSS, IDSQ, IDQ and the VGSQ. First we decide the drain current, that should be, as we said, half of the maximum value IDSS. Okay, half of the maximum value IDSS. So in that case, uh, so IDSS. Now with respect to that, you have, suppose from the manufacturer or from this equation, you do have this transfer characteristic. So with respect to IDS by 2, you can find VGS corresponding to it. Okay. Usually, both IDSS and VGS are not defining in isolation. Maybe sometimes you first decide VGS and correspondingly you define IDSS. But let's say if you take VGS, because you want to set this difference to be almost around 1 by 2, you can see this is if I keep VGS is equal to VP by 4, suppose if I keep VGS is equal to VP by 4, this is going to be 1 minus 1 by 4, that is going to be 3 by 4, that is 9 by 16, that is almost 9 by 16 is almost around half of it. So if you take VGS is equal to VP by 4, that will be almost around at the center. That is how we decide the Q point. So this is a line which is drawn from the origin to that point, and this is our Q point. Fine. So the thing is, idea is first we decide IDSS. ID is equal to IDSS by 2. And correspondingly we find out VGS. So that decides the operating point. Fine. Correspondingly we decide VGS. So fine. So this was all about the